Hey guys, Fitness Science here and welcome to part 3 on the series of steroids. As you know, in part 2, we discussed the androgen receptor and how it actually works, as well as how steroids can bind either strongly or weakly to the androgen receptor to increase muscle mass. But in this third episode, as promised, we will be making the exact structural modifications to steroids in order to make them more anabolic or more androgenic, as well as more or less potent at binding to the androgen receptor. But first, we need to understand one key point, and that is that all steroids are derived from one key molecule, which is testosterone. Yes, every steroid is based on testosterone with slight chemical tweaks in order to make it more or less potent. And because there are so many chemical tweaks available, there are thousands of different types of steroids. Testosterone is a 4-ringed structure, 4 carbon rings, A, B, C, and D. A, B, and C are 6 carbons, so they are shaped like hexagon rings. And ring D only has 5 carbons, so it's actually a pentagon ring. And in total, testosterone has 19 carbons, 28 hydrogen atoms, and 2 oxygen atoms, with each carbon atom being named 1 to 19 according to its position on the ring. So keep these positions in mind when we start to manipulate these. Now, as discussed in part 2, testosterone is both anabolic and androgenic, anabolic being pure muscle mass building effects and androgenic being everything that's not muscle mass, so things like increasing your prostate weight, your body hair, and deepening your voice. And this is very important because as a man progresses through puberty, testosterone is the thing that gives us both masculine effects as well as an increase in body weight and muscle mass. If one of these things was out of balance, we would either have too much masculine effect or too much muscle mass, and this doesn't happen. So testosterone is balanced at 1-for-1, just as anabolic as it is androgenic. But DHT, which is the more potent form of testosterone, which is when testosterone is reduced by 5-alpha reductase, the enzyme 5-alpha reductase, that is actually very androgenic. So any steroid, when it's modified, that cannot convert to DHT is actually going to be a lot more anabolic, and this is in the literature called disassociating the anabolic and androgenic effects. In other words, creating a chemical structure that cannot be turned into DHT by 5-alpha reductase is going to mean that steroid is very, very anabolic. And this is exactly what researchers tried to do after testosterone was discovered in the 1930s. Over the 90 years of research until today, keep in mind a lot of this research was done for people with clinical muscle wasting diseases where they needed to inject them with steroids to boost their muscle mass because they were wasting away due to some underlying pathophysiology. But through all that research, we found out some pretty interesting things about modifying testosterone. In summary, they are: removing the oxygen to hydrogen group at carbon 17 completely eliminates all androgenic activity and stops the steroid being converted to DHT. Now, whilst in practice that actually sounds like a good idea to boost the anabolic potential of the steroid, it actually removes the ability of the steroid to bind to the androgen receptor. So we actually need that for binding because it's kind of a balance. You need to both have anabolic activity, but you also want to make sure it actually binds correctly to the androgen receptor. Removing the double bond between carbons 4 and 5 significantly increases androgenic activity. And in fact, DHT, which we know is very androgenic, has no double bond between carbons 4 and 5. Removing the carbon to oxygen bond at the 3rd carbon position. Removing this significantly decreases both androgenic activity by about 40%, but it also reduces binding significantly because that oxygen atom is very important for binding, and it can actually reduce the binding of the steroid by 5 times. Removing the methyl group at the carbon 19 position. Now, a methyl group is a carbon atom surrounded by 3 hydrogens, so removing that at C19 significantly reduces androgenic activity and really boosts up the anabolic activity and anabolic potential of the steroid enormously. Modifying the A ring to add another ring to it, so actually modifying the structure quite substantially, or by introducing an oxygen atom into the carbon 2 position, leads to a significant increase in anabolic activity. But interestingly, studies have shown that the substitution of an oxygen atom at the C2 position is not required to increase the anabolic potential of a steroid if there is a double bond from carbons 4 to 5. But the huge ring at the front of the steroid is a lot of bulk, and that doesn't fit very well into the androgen receptor pocket very well. So these types of steroids have a very weak binding affinity to the steroid receptor. Adding another methyl group at the C17 position, which is called 17-alpha alkylation, significantly boosts anabolic activity and is probably one of the most important changes to a steroid structure in terms of anabolic potential. The main reason is because adding a group at the C17 position prolongs the anabolic effect hugely, and it is also one of the key substitutions required to make a steroid available to be taken by mouth. This is because the methyl group at the C17 position slows down the ability of the liver to make it inactive and break it down. Adding a double bond from carbons 1 to 2 significantly decreases androgenic activity and boosts anabolic activity. Adding another methyl group at carbon 2 boosts anabolic activity. And one reason is because a methyl group at this position seems to stop the ability of aromatase to be able to convert the steroid to estrogen, and that's why the anabolic activity may be boosted, because it's actually not being converted to estrogen. Adding an oxygen to hydrogen group at the C4 position can make a steroid up to 6.9 times more powerful. Adding a methyl group at the C7 position significantly increases anabolic activity, and in some studies up to 1,000 times. And the reason is because a methyl group at the carbon 7 position stops the ability of 5-alpha reductase to work on the steroid, so it cannot be converted to any DHT derivative, and therefore the androgenic potential is lost. Not only this, but a methyl group at this position makes the steroid a lot more flat in structure, and a flatter steroid can bind into the androgen receptor pocket a lot more easily, as discussed in part 2. Adding double rings from A all the way up to C increases anabolic activity, and also means the steroid cannot be converted to estrogen. And with all that, now we can start to understand why some anabolic steroids are more potent than others. Double bonding carbons 1 to 2 are things like turinabol, equipoise, and dianabol. Adding a methyl group at C2, which is more anabolic, are things like drostanolone. Anadrol, dianabol, and halotestin all have a methyl group at carbon 17, so all of these are quite anabolic, because as we know, adding a methyl group at the 17th carbon position significantly prolongs and lengthens the amount of time that the steroid is bound into the androgen receptor and able to increase muscle mass. Oxandrolone, which is Anavar, adds an oxygen at carbon position 2, which increases the anabolic activity, essentially by changing the stereoelectric environment of the steroid, and this increases anabolic potency. As I said before, DHT loses the double bond between C4 and 5, so it is a lot more androgenic than anabolic. Mibolerone, which is check drops, and Ment, which is Trebolone, are examples of steroids with a methyl group at C7, so carbon position 7. This both increases the binding affinity as well as their anabolic potential. Trenbolone adds double bonds all the way from rings A to C, and like I said, this significantly flattens the steroid structure and means it can bind into that androgen receptor pocket with so much more affinity and really is a lot more potent. The presence of these double bonds all the way up the steroidal backbone also means that Trenbolone can't be converted to estrogen, which only serves to boost its anabolic activity even more. And finally, stanozolol, which is Winstrol, and danazol are steroids that add a ring to the ring A structure. Now, these studies are a bit mixed as to how potent Winstrol is with a big ring at the front of it in terms of anabolic activity, but we do know they're pretty weak binders overall because that big ring doesn't really connect very well to the androgen receptor and doesn't allow binding to a very strong degree, so it's actually a weak binder. And there you have it. We have now taken a comprehensive look at the pharmacology of steroid structures and how we modify them to make them more anabolic. Now, in part 4, we're going to take all of this and start having some fun in designing our very own steroid, and we're going to actually design the world's most powerful anabolic steroid. And you guys get to name it. Yes, that's right. The comment with the most amount of likes will actually get the right to name this steroid that we create. Now, of course, this is all just for fun. We're not actually making this thing, but in terms of naming it, you guys get it. So the comment, most amount of likes, you get the name. Thank you so much for watching part 3. I will see you in part 4 where we make the world's most anabolic steroid.